and which and been motivated by earlier wonderful works by Bajanov and Sergeyev, and also Spiridonov, and which in turn goes back to all these earlier works on integral models, which I'll come to later, all the way down to Baxter. And also, well, I cannot resist the temptation to mention that our paper, which appeared just yesterday, with Till and Florian, who are in the audience, I guess, and also another Yuting fan, another postdoc at IES. And this paper is about well, first of all, the Young invariant deformations of N equal 4 and ABGM. And we had the Grassmannian formula, which appeared in Tomek's talk yesterday. So we are going to make, and if I have time, I'm going to make a brief contact with what we did here. And in fact, all these things fit nicely into the framework of trying to understand integral models, starting from the viewpoint of supersymmetric gauge theory. So let me begin with the introduction. And we already heard a nice talk about the ocean of integrability. And well, there has been tremendous development in this area of understanding, in particular, N equal 4 dimensional N equal 4 supersymmetric Yang-Mills theory, and there are gravity duals, and then people try to generalize it to various different theories, and there has been a lot of activities. But I should remind you that, well, of course, this is a huge ocean, and there are a lot of interesting stuff there, but the world is huge, and this is not the end of the story. And there are other parts of the world. In fact, the sort of looks somewhat like Atlantic, and as a person from a small island somewhere here, I cannot resist the temptation to mention that there are other parts of the world. And and then, well, I have been working somewhat around this area, and that's the field of supersymmetric localization. And while there has been already several talks on this subject, and people have already making contact with supersymmetric localization with the integral models. But at least the point is that it's about exact computation of partition functions in supersymmetric quantum field theory. Exact means we have some exact integral, exact numbers, and these things coming out. So, and in fact, the technology is so nice that you don't have to learn too much about quantum field theory to at least derive some numbers. If you have a good graduate students, you can try to learn the subject, and he could learn everything relatively easily. And if you have your favorite theory, like a 4-dimensional SQCD with some crazy matter content, adjoint matter, or things like that, tensor matter, and then you can write on the integral expression immediately in 10 minutes or so. And then, of course, you have to solve the integral. Sometimes you can do analytical methods, matrix model techniques, even numerics to solve it. And that's a very powerful technique to solve these, to learn about the supersymmetric quantum field theories. So we have tons of expressions, tons of new results, tons of new numbers. So that's, I think, is amazing, and this is a huge field. However, this is not the end of the story. But first of all, just obtaining exact results does not mean that we have integrability is there. So integrability does not just mean a sequence numbers, but there is some structure behind it. So there's a natural question if there are any integrable structures here. And of course, there has been many activities. And the answer is that there is certainly integrable structure here and there, and we already heard several talks along that direction during this conference. So what I'm going to do today is to add some example, a simple example, where there is again a connection between some results from supersymmetric localization, some results about exact computation of partition functions of 3-4 dimensional, in my case 4-dimensional supersymmetric gauge theory, and then how it's related to integral models. And in particular, the goal is really to, well, since this is a conference on integral models, my goal here is not really to understand quantum field theory, but rather, let me pretend that I use quantum field theory as a tool to construct new integral models. So that's the thing I'm coming to. And well, this is more or less represent my title of my talk, so which is to understand integral models from supersymmetric quantum field theory. And also, I should also mention that, well, here it might look like that all these things are disconnected, but it's not really the case, at least in some way. And you can try to go here and try to go around, and then there are some. This is not a straight line because there are some differences, etc., difficulties. There are a lot you have to travel around, and but there is in fact some parallel very mysterious parallel between the story which are developed here and some of the stories developed in the context of scattering amplitude or four-dimensional echo 4, or and which people are generalizing now these days to ABGM theory. So towards the end of my talk, if I have time, I'll mention these connections. Okay, but let me start with this part about constructing new integral models from four-dimensional theory. And I called it the Gauge-Bethe correspondence because it's a correspondence of the Yang-Baxter equation and the gauge theory. But this is just a slogan, so let me try to explain the content. And of course, this is the last day of the conference. I know people are tired already, and especially this is the talk after lunch. So let me try to begin with something extremely elementary so that people get at least something. So let me start with some lattice. So this is some lattice, and well, what do you think of it? And then, of course, depending on the background, people come up with a different answer. And one answer is that, well, it's some lattice on which you can define some statistical mechanical model. So it's a lattice. So it has vertices, both vertices, and edges connecting them. And at the vertices, we have spins, so which I collectively denoted by this at the vertex. And of course, the lattice has edges connecting them, which means that there is some interaction, nearest neighbor interaction, which I denoted by this. So this is the Boltzmann weight or energy associated with the nearest neighbor interaction. So here we have an edge connecting two vertices. And well, here also, for later purposes, I also included a self-interaction between at the particular vertex. So this might have several different components, so there could be several different interactions among different components of the spin. Well, this could be continuous, discrete, etc. But anyway, this is what it is. And of course, the partition function, everybody here knows how to define the partition function. It's just to take the Boltzmann weight. I'm going to set the beta equals to 1 more or less afterwards. And then we are going to sum over all possible spin configurations. So this is the partition function of the statistical mechanical model. Now, the reason that I said somewhat trivial thing is that actually, if you are a supersymmetric gauge theorist, you might try to regard it as something rather different. So if you're a gauge theorist, you might want to regard this as some defining data of a supersymmetric gauge theory. So I want to do supersymmetric gauge theory starting from this. And one way to do that is to use the notion of the Quiver type gauge theory. So what does it mean? Well, at each vertex, there used to be a spin, but instead of the spin, I have a gauge group. So let's call it the G of V at a certain vertex. So that means that I have a gauge field. It might have several components, mu, where mu is supposed to be the Lorentz index for some Minkowski direction. And this x is a point in this Minkowski space. So what happens is actually that in addition to this two-dimensional plane, I have something completely different, complete orthogonal, which is this RD, 1. And all these things take dynamics. The dynamics of these fields take place in this Minkowski space-time. Well, I could, in fact, I'm going to later compactify this. But anyway, so there's a manifold here. So that's the degrees of freedom associated with the vertex. And then there is also a matter, something associated with the edge. So edge is, corresponds to a matter, some matter charged under two gauge groups at the two endpoints of that edge. And then in the end, well, you can try to do something very similar to the Boltzmann weight here. So that but sum of nearest neighbor interaction, there is self-interaction. And you can write under some similar thing. In fact, you can write under Lagrangian. So that's this Lagrangian. So this is self-interaction. So for example, there could be kinetic term for the gauge field. And then there are interactions. They might couple through covariant derivative to these fields. And then so this looks very similar structure. And you can define the partition function by integrating over all these degrees of freedom. So this is somewhat similar. They are slightly different, but it's somewhat similar. The huge difference is that it used to be that the spin was typically some Z2 or some even U1 or some simple variable. But here, instead of having some parameter like that, we have a function which takes value in the Minkowski spacetime. But the point is that if you define supersymmetric quantum field theory this way, it really looks like some version, very sophisticated, very complicated version of the statistical mechanical model. But of course, this itself is not too, well, you might object that this is a very formal observation. And in the end, I will come back to, I'll come back to this for the statistical mechanics afterwards. But let me try to pursue this sort of analogy or part of reformulation of understanding reformulation of quantum mechanics, quantum field theory. And but so far, this is very vague. There are some gauge groups, some dimensions. So for specific, well, for concreteness, I can specialize to the particular case of four-dimensional supersymmetric gauge theory. So I want some supersymmetry for doing some computations. And I take the four-dimensional equal-1 theory, which is, of course, one of the most familiar theories. And for the gauge groups, well, I'm going to take simply SUNB for at the vertex B. And I'm going to, in the end, take the rank of the gauge group to be the same everywhere. So we have SUN gauge group here, SUN gauge group here and there, everywhere SUN gauge group. So in this case, there are, I don't know, 25 sides. So we have, this is a huge gauge theory. This is a gauge group SUN to power 25, for example. Now, and also, let's see. Well, since I have the supersymmetric theory, there used to be a gauge field here, but of course we have to supersymmetrize everything, and this gauge field becomes a vector multiplet. Now, and also there is some bifundamental. Well, okay, so for the edge, I'm going to associate some matter which is charged under the two gauge groups. And I didn't specify the representation, but for my purpose, I'm going to take the so-called bifundamental representation, where if you have two vertices, there is a corresponding SUN times SUN gauge group, and I take some matter which transforms as a fundamental with respect to one of the gauge groups, and anti-fundamental with respect to another gauge group. So it's just a matter in some representation. But the important point is the charge with respect to these two gauge groups, and only for these two gauge groups. And also the important point that since I have four-dimensional N-1 theory, four-dimensional N-1 theory is chiral, so we need to specify the orientation. So n bar is not the same as n bar n. So you have to represent that graphically. So I choose some orientation to the arrow. And consequently, you have to orient in some way. But I have chosen the convention. For some reason, I don't explain too much that everything is going around clockwise or counterclockwise around the faces. So this is, and then you can take this as a defining definition of four-dimensional N-1 theory. Well, you have to be more precise, you have to specify the superpotential interactions, but you can also do that here. Now, why is this useful? Well, I haven't really given the answer, but let me try to pursue this analogy. And well, let's come to integrability. So far, I just discussed on generic lattice, and there is no integrability whatsoever. So where does the integrability come from? Well, of course, well, for that, we have to remind you, again, something very elementary about Yang-Baxter equation, which I'm sure everybody knows. But just to emphasize that the Yang-Baxter equation can be written as a product of three R matrices. And so it's one R matrix for the intersection. So I'd like to ask the question of, is there any gauge theory counterpart of all this? And well, in order to see that, you have to understand this a little bit better. First of all, what is there in some data which comes into this? And one data is that R matrix is associated with some crossing, first of all. And it has four indices, which are denoted by ABCD here. It has four indices. That's a crucial ingredient. And then, well, of course, there is another ingredient, which is to take a product of two R matrices. And everybody knows how to take a product of matrices, namely take a product, and then sum over the corresponding variable. So in this case, there is a variable C, which is in the middle. So if we glue these things together, we sum over these parameters. Whereas here, it was a fixed parameter. And once we know what the R matrix is and what how the gluing works, we can write down the theory. We can write down the Yang-Baxter equation. Now, let me try to translate it into gauge theory language. So first of all, we already learned a lesson before. So in the statistical mechanics, you have spins at the lattice, but now that's replaced by the gauge group. That was the story. So here we have some degrees of freedom which are the spins, so that should be replaced by gauge group again. So this R matrix should be replaced by something which has four gauge groups. But something could happen in the middle. And there are many possibilities. And in fact, it's interesting to try to exhaust all the possibilities where the story I'm going to talk about works. However, there is one simplest choice. Yes. 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 Okay, so okay, okay. Yes. Yes. Mm-hmm. Okay. Okay. Yes. Yes. Well, I'm not okay, but this is this is more or less somewhat different. But okay, but it's not that far different. I mean, for example, I'm not doing lattice gauge theory, for example, but there is a connection to lattice gauge theory in the sense, but this is not lattice gauge theory as it is, for example. So it's a little bit different, I would say. Yes. Yes. Yeah. I mean, right. So I mean, right. So far, everything I say is analogy. In fact, what I'm trying to do is to try to push forward the analogy to the far end, and then everything else, from that point, you can go to the integral models without any analogy. So that's what I'm going to do. Well, I could present the result in the completely opposite direction. Here's the answer, and then here's the integral model. But I try to do that, do the opposite direction in order to give a better idea of why I'm doing that. Yes. So the theory corresponds to R matrix. It turns out it's just this simple quiver. So we have 4 vertices. And if you concatenate 2 R matrices, namely to take up 2 product, and then it just means that you have to concatenate 2 R matrices. So you have this, you prepare 2 such things and glue them together at this vertex. So that's what's represented here. But of course, you have to be a little bit careful because here there was a difference between the variables over which we sum, and there's a variable which are fixed throughout. And taking the product really means to take the product and sum. So we have to distinguish between the spins over which we sum, fixed spins, and the dynamical spin. And there is a counterpart of that in gauge theory, which is that we have a gauge group, gauge symmetry, which is dynamical, and consequently we have to sum over. And we also have a flavor symmetry. And so these are external gauge field. So they can be non-dynamical. And the partition function does depend on that fixed parameter. And then you can try to make this, and then I represented the difference between square and circle, which is standard in some literature. And in this case, for example, there are 4 things, fixed parameters. So consequently, there are only 4 fixed squares, 4 fixed flavor symmetries. And I chose this to be flavor, also gauge symmetry. That's the thing we integrate over. So this data depends on external data for all these 4 gauge groups. And when we take a product, we have to sum over this. So I replace this by gauge symmetry. Namely, the taking the product of 2 R matrices corresponds to take a product of completely decoupled gauge theory, and then try to gauge the flavor symmetry to promote it to the gauge symmetry. So that's the thing we call gauging. So gluing corresponds to gauging. Now, once you understand this, well, you can try to see what happens to the Yang-Baxter equation. And since I know the quiver, this is the quiver for the R matrix, and we can just write on the Yang-Baxter equation. And it seems that the statement is then that these 2 theories are the dual to each other, in some sense. They describe the same physics, so that's the statement. And unfortunately, this as it is doesn't work. In fact, if you try to look for the literature, well, first of all, this is some theory which the gauge groups SUN to 4s and flavor symmetry SUN to 6, for example. And you might try to go through the literature and try to see if there is any known duality of this sort. And unfortunately, there is no known such duality. So maybe we are doing something completely meaningless, except that, well, there is something for rescue, which is that, well, maybe this in itself might not have appeared in the literature, but it might be the consequence of another duality, which is already known in the literature. And maybe by combining these dualities, we might be able to derive the duality of this sort. But then I need some basic building block. What is the basic building blocks? What is the basic duality? Well, since I have 4-dimensional N-1 supersymmetric field theory, I could open the quantum field theory textbook and then just 4-dimensional N-1 and search for the duality. And then you find out that there is some duality known as the Seiberg duality, which is one of the most basic dualities in supersymmetric quantum field series. And of course, let's see, if you know about Seiberg duality, well, you know it. And if you don't know about it, please don't bother too much. It's some duality. And for my purpose, it's just a statement that this quiver, this particular quiver, is the same as that particular quiver. Or more precisely, the gauge theory described by this quiver is dual to the gauge theory described by this quiver. Well, so let me explain a little bit more. So here, I'm taking the Seiberg duality with this gauge group SUN. And then there are two arrows and two arrows going out and two arrows coming in. They represent the quarks and antiquarks, if you are familiar with SQCD. And then after Seiberg duality, the orientation of arrows are now completely opposite. So that corresponds to having dual quark, which has the opposite gauge charge. And also, what's interesting is that we have some arrows here, which look like a singlet from the viewpoint of this gauge group, but nevertheless charged under Flavor symmetry. And in Seiberg duality, there is such thing known as the meson. And meson is something represented by these lines. And in particular, there is a close triangle here. And the meaning of the triangle is that you can take a product of these bifundamental fields and then take a trace and have a gauge invariant operator. So you have a superpotential term, and that's the familiar type of the superpotential in the Seiberg duality. But anyway, there's a non-duality. And, well, you can also represent it this way, where there are two lines to here and there. So the question is whether we can use this as a basic building blocks and then use this several times to arrive at something like this and arrive at something like that. And the hint is that this is something very nice. And in fact, this is already very close to the naive R matrix, which I was talking about previously. So you can try to do the same game, except that we use the same thing. So we place the R matrix here and there, except that when two arrows collide in the opposite direction, I'm going to eliminate it. And the physical meaning of that is that there is a matter here, and there is another matter here. And if you take a product, there is a gauge singlet. So you can take a trace, and you can write on the superpotential term corresponding to that. And it's quadratic. It's a mass term, so you can integrate them out. So as long as you're interested in the IR behavior of the theory, you can forget about that. So by using that logic, I eliminate some of the arrows when we combine these three R matrices. And then I obtain this figure. So is this a good theory? Is this a good correct duality? And in the end, and fortunately, the answer is yes. So I could use the Seiberg duality a few times. So for example, I could take a Seiberg duality with this vector, this blue node. And maybe you don't remember the transformation rules, but the transformation rules first change the orientation of all the arrows coming in here. So that this blue vertex is now here. Oh, sorry, it's fractures, but here, yes. And then you change the orientation in the opposite direction. And then there are some two lines here. You add some of the lines, just following the rule I gave previously, this rule, but just only locally. I apply this locally to this huge Quiver diagram. And I obtain this graph. And in the next week, I could do the Seiberg duality for this blue dot, and so on. And if you repeat it 4 times, in fact, I come back to this Quiver. So that means that the Yang-Baxter equation, which is this duality, Yang-Baxter equation, which is now translated to the duality statement. So I might call that Yang-Baxter duality. The Yang-Baxter duality is actually simply a consequence of the Seiberg duality done 4 times, which I think is an amazing result. And in fact, very interestingly, I'm not at all the first person to discuss this sequence of transformations. And very interestingly, it was known, well, first of all, this transformation was known in the context of statistical mechanics as a star-star relation in my understanding. And that was discussed in 80s and 90s in Baxter Bajanov, which I referenced here. And so they found this relation. And interestingly, they also found that you need to include these lines, which is crucial for Seiberg duality, namely the mesons. So I would say, actually, the Baxter and other people, and Bajanov, these people were somehow knew about the mesons, presence of mesons of Seiberg duality, even before Seiberg discovered Seiberg duality. which I think is amazing. Maybe you might have not realized it, but that's the historical lesson I'm getting. So sometimes if you are doing integral models, you might be secretly discovering some important aspects of integral models, sorry, of the supersymmetric gauge series. So but anyway, and then there is some of the earlier papers definitely have this figure, that you can use the star-star relation to derive the Yang-Baxter equation. In fact, that was the reason why people are interested in, yes?
Sorry, I might have missed that. Why are there two lines with no arrows?
Yeah, okay, so, right, so here, for example, here?
Yes.
Yeah, that's right. So for this, you put the R matrix here, right? So you put the R matrix here and there. So what happens is that here, this line is just this line, but there is another line here, in fact. And then if you put another thing here, so I have to squeeze it in and then put it here. And I have another arrow here. There are two arrows, but they go in the opposite direction. Yes. And the rule is that if there are two arrows connecting the same two dots in the opposite direction, I delete that.
I know this diagram very well for very different contexts.
Okay, I see.
That's why I'm asking.
Oh, I see.
Cluster algebra is exactly that relation.
Oh, yeah.
Same thing.
Oh, yeah, okay. Yeah, in fact, this figure appears in a number of different contexts. For example, people try to discuss the connection between bipartite networks and the resistor network, for example. Oh, maybe that's the context, for example. And another context I'm going to mention is that there's a connection there's a connection between integrability and the scattering amplitude, which partly appeared in the atomic stuff yesterday, for example. And if I have time, I might be coming to that. Yeah, in fact, interestingly, this figure appeared in many different contexts. But now I'm making the statement about supersymmetric gauge theory. And then, so far I haven't done any computation, just some graphical rules, but already know that this is a duality. Well, strictly speaking, if you are really field theory affectional, you might a little bit complain about whether this has a really fixed point, etc. But these are always usual. There are some, I must admit that there are some very subtle points about the existence of fixed point about this quantum field series. But let me feature price to almost any discussion about Quiver gauge theory of this sort. But let me not go into that. But basically, it's just a sequence of Seiberg dualities, and we are very confident about Seiberg duality, so this duality should hold. And so in the end, I have been making the analogy, but in the end, I obtained something very definite, namely just the duality state in the supersymmetric gauge theory. Now it's time to go back to integral models. Now from here, I don't have to make any analogy. And let's go back to integral models. So what does it mean to go back to integral models? Well, when we start with the statistical mechanics and replace that by gauge theory, I replace the spins by the fields, which takes part in the Minkowski spacetime. So if you want to go back, we have to eliminate the dependence on the Minkowski direction. And in fact, that's what people do in the localization story, supersymmetric localization. So first, the first consequence of the duality is that since these are two dual theories, so I denoted the two theories here, the theory here and there, as a theory corresponding to this composition of the R matrices. So there is some theory, and it's another theory, they are dual. And since they are dual, the partition functions are simply the same. Well, except that this itself is not really a Yang-Baxter equation. For example, Yang-Baxter equation says it's a product of three things, but this is just one single number. So you have to make sure that these things factorize, for example. And fortunately, that is guaranteed if you compute this partition function from supersymmetric localization. In other words, this is here, this circle here was concatenating the quiver, which corresponds to gauging in supersymmetric gauge theory. And it's known that, it's not hard to imagine that it corresponds to taking the sum product here at the level of the partition function. So namely, the product of gauging, operation of gauging and computing the partition function sort of commute, and it's compatible. So here we have a sum. In other words, you have to integrate a sum over the corresponding variables, which becomes dynamical. In other words, when some of the gauge fields becomes dynamical, we have to sum over that. And you do the same thing for the, here you have to sum over the remnants of the gauge field which we are gauging at the level of this partition function. And not only that, we also have the structure of the nearest neighbor interaction. Well, namely, this was the partition function which appeared in one of my previous slides. If supersymmetrized, we have to include fermions too. But anyway, this is the structure. And there are gauge fields at the vertex and some chiral multiplet at the edge. But then there is some supersymmetric localization. And in the localization I'm going to use, the gauge field becomes, this is a function on the Minkowski direction, simply becomes a constant at a certain point. And all these bifundamental chiral multiplets, the scalars part, go to 0 at the localization saddle point. And then what happens is that in the end, there is no, you don't have to integrate over this because there is a delta function here. And instead of doing the function now integral here, you just sum of the spins. Which spin is just the remnant of the gauge field when you do the localization. Well, Lorentz index, yeah, in fact, it's crucial that the Lorentz index disappears, yes. So here we have a mu. Well, actually, okay, so this is, okay, I agree that this is a little bit schematic. In fact, you have mu here on the left-hand side, but mu, it doesn't. Right, so in fact, for example, I'm going to discuss for this theory S1 times S3, for example. And then what happens is that you have a gauge field component along that S1 direction, and you can compute the holonomy along that direction. And that will be this parameter sigma. Yeah, I agree, this is a little bit schematic. But in that case, it will be A0 which becomes constant, and all other components of the gauge fields become trivial. Because, okay, maybe I should first explain what geometry is going to. And that's not the generic property of the localization, but at least in the specific localization I'm going to talk about, that holds at least. And once you have the structure, well, this is really the statistical mechanical model, and all the variables now live just on the vertices. So this is exactly the type of the statistical mechanical model I was talking about. And you can compute the various partition functions. Well, let's see. And this is very good because the choice of the partition function is not unique. And that's why the statement, the gauge theory duality statement, is much more powerful than the particular Yang-Baxter equation. So you can this is a duality statement. You can take various different manifolds and compactify and accept various different quantities, and they should give the same answer. And so there is a choice as to which partition function we choose. And so if you choose a different partition function, it gives rise to different integral models. So actually, this duality statement gives rise to not just one integral model, but a sequence of integral models. So that's the power of this duality. And in practice, one of the most powerful quantities which are defined for four-dimensional equal-1 series is this partition function, or index, people call it, on this manifold, S1 times S sigma ZR for this length space, some discrete group action, which I computed a few years ago. And I'm not going to go into any details of this partition function, but what's important for my purpose here is that it depends on some variables. First of all, it depends on this R. This is an integer, or the order of this length space. And also, it depends on n. OK, so that was implicit here. But I have a Quiver gauge theory where all the nodes are SUN gauge groups. But that n is some number. So that's this n. And there are some fugacities which you can put on, some parameters, which is a twist along this S1 direction, which is denoted by PQ. And moreover, there are some parameters which correspond to the R charges of the chiral multiplet. So the partition function depends on the R charges of this chiral multiplet. Then the chiral multiplets of the things associated at the edge. But it turns out it's known actually from almost 5 years ago so that R charge of this Quiver gauge theory can be written in terms of variables associated with some lines written on this graph. And actually that's the same as that can be identified directly as a spectral parameter. Well, for example, I'm not going into the details, but for example, there is a constraint that if there is a superpotential term, and the sum of the superpotential, the R charge of the fields in the superpotential should sum up to 2, because that's the convention. And that really looks like the angle-like interpretation of the spectral parameter, where if you have an angle, they sum up to 2. So there's a natural counterpart of the spectral parameter, and that's the R charge. And so, right, so this sigma, what I'm writing very schematic right here, sigma, so that will be the spin at the vertex. And the spin, in this case, in this particular case, is a holonomy of the gauge field along these directions. And since it has a continuous holonomy, and it could have discrete holonomy here and there, and it could, depending on the length of the gauge groups, it has many such components. So it has continuous variables, n-1 continuous variables, as well as n-1 discrete variables. So it's actually a lot of complex spin system where you have both mixture of continuous and discrete spin systems, but anyway, so that's the model I obtained. And it turns out that the resulting model is, as far as I know, one of the most general solutions to the Yang-Baxter equation known in the literature. Surprisingly, I don't know much about this integrable structure, but I just do the computation using this logic, and it seems to be rather general. And I'm not going to give you the formula. In fact, you're not supposed to read this. But important point is that there's some formula here and there. And there's there's discrete spin, continuous spins, and then there's complicated Boltzmann weight, and it takes some form. And there's some function. Well, maybe I should mention that there's some function also, elliptic gamma function, which depends on two parameters, P and Q, for example. But anyway, so there's some complicated thing, and with the continuous discrete spins. So I would bet that it's extremely difficult to try to find this by some other method. Now, in the remaining minutes, let me try to make some comments about the model I discovered. So first, well, this is some complicated model, but can you simplify it? And of course you can by taking various specializations, various specializations. So I could take the limit where some of the parameters go to 1, or some of the parameters go to 0. Or maybe these P and Q are like a quantum Q for the quantum group, so it's a quantum parameter. So as you know, it's sometimes very useful to, interesting to take the limit of root of unity limit of those parameters, etc. And in fact, Bajanov Sergeyev constructed the model for when this R equals 1 a couple of years ago, which was in the reference at the beginning. And there, they amazingly derived a connection to a number of different interval models by taking various limits. I hope this is correct, and all the way down to the Ising model, in fact. So this is, and so as I said, here we have the parameters P and Q. And so, and in some cases, in the simplest cases, when this parameter n, so this is the limit where R goes to 1, and I could set n to 2. And in that case, it's known that the resulting thing is related to the algebra defined by Skryanin for SL2. And so I would expect that the similar should hold for SLN generalization by Cherry. And there is a generalization by Cherry-Donic. But that's still the case for R equals to 1. And, but here, I have there is another index R, and I have the suspicion that this corresponds to another variable, another label for the quantum group itself, not the representation label. So for this, R is in integer. So PQ are continuous parameters, R is in integer. So there might be a group. It might be suggesting the existence of a group like that. So I have the R matrix. So the problem is to identify the underlying quantum group-like structure, which gives rise to that as an intertwiner. And I have no idea what this group is. But somebody, in fact, Michio Jimbo told me that there is some papers by Feige and DESY, which sort of looks like that. So maybe that could be related, but well, maybe some experts might be familiar with it. But anyway, so the point is you can discuss various reductions. And this is where integral model people and the supersymmetric gauge theories could gather together. Because in some cases, the reduction is known only to integral model people. Or sometimes there's some reduction which only supersymmetric field theories have done. So we could try to ask the question of say, this is some reduction which I did, which is known only to supersymmetric field theories, and try to ask the meaning in terms of integral models so vice versa. And then there's, and actually there is an interesting point about this, especially there is some model, which is a color pots model, that you can derive this from this reduction of this thing. And that is actually interesting, because there's a paper by Ed Britton in 1990 where he was trying to understand the quantum group from the Chern-Salmon theory. And he was listing several questions, and one of them is that first understand the origin of the spectral parameter. And as I explained in my story, this spectral parameter is just R charge, so I think this is done. And then there's a comment about how the spin models probably allowed this entry 24. This is actually the Karl Potts model, so that was 1986 or 7 or so. So that was recent when Whitney wrote this paper. And it's more or less done in the sense that I can derive the Karl Potts model as some limiting procedure of gauge theory. But you can also try to understand the meaning of the reduction gauge theoretically. But this is half done, I would say. And then there is also, he was saying that the physical values of Q, so you have to analytical continue in Q, etc. But in my story, Q is really a fugacity, so you can, it is completely free to analytical continue. So I might claim that I might have solved some of the problems, except that, as I said, I didn't, Whitney was also trying to raising the question of understanding the quantum group structure directly. And since I don't know the group, in fact, instead of solving the problem, I discovered the possibility of enlarging the group-like structure to one more parameter and one integer. However, I should mention that there is an interesting paper by Costello trying to understand the quantum group structure in a completely different context. Okay, so let me make one more comment. So I guess a lot of people here are interested in the Gauge-Bethe correspondence, which we refer to Nikita. And there the story is that there is a two-dimensional 2,2 theory and the twisted superpotential for that. that gives rise to the Yang-Yang function whose derivative gives rise to the Bethe-Ansatz equation. So this is the correspondence. And this correspondence is somewhat similar to the Gauge-Bethe correspondence as mentioned. However, the story, if you look at details, the actual details are very different. I mean, the actual details are very different. We have 40 theory with a row, right? So 4 supercharges with the actual groups are different, etc. And in particular, well, of course, each has advantages and disadvantages. But in my case, the one advantage I could say for my story is that it gives rise not to the Yang-Yang function, but directly the R matrix in the Yang-Baxter equation. So it actually is useful for constructing new integrable models. But there is some similarity in the sense that the integrable structure, in order to see the integrable structure, you have to compare different series, different quivers for different quivers, namely different gauge series. So actually, integrability is not in a single series, but in order to see the integrability, you have to consider a set of series, and then the integrability is there. So I might call it the integrability in series space. So we have to, in order to understand this, we have to change the mindset of studying a particular gauge theory, but rather to try to take a collection of supersymmetric gauge series and see what kind of structure is there. And finally, I guess in the remaining minutes, I could comment on the similarity with scattering amplitude. Well, so here I have a quiver. And so this was the quiver corresponding to the R matrix. And however, actually, let's see, we have, well, in my paper with Dancy, and also there's an independent paper with Sebastian Franco in 2012, there is a story of, so I associated, of associating a bipartite graph for here. So let's see, so here it's more or less like a dual graph. So basically the story is that there is a bipartite graph, which is defined as a dual of the Quiver diagram, except that in this case, the rule is a little bit more subtle. You don't, there is a line, so right, so there is a vertex here that corresponds to face here, and there are 4 vertices correspond to 4 faces here. So this is more or less like a dual, except that I don't draw 2 lines here, and that's a rule, which was a subtle rule, which I discussed in the paper with Dan C. But anyway, there is a rule for associating, well, I could start either way, but I could start from this bipartite graph, which in this case is the Prana bipartite graph. So this is the type of the graph discussed by Postnikov. And then I could define a quiver from that, and then consequently a quiver gauge theory. So there was already their story. And combinatorially, the point is that the quiver I was writing can be translated into this bipartite graph. And bipartite graph appears in a number of different contexts. And in particular, Seiberg duality, okay, and different people tend to interpret this in a different language. And in the gauge theory language I have been using, the Seiberg duality corresponds to this. And what I was calling Yang-Baxter duality, the duality corresponds to Yang-Baxter equation, looks like this change. So I was writing the quiver previously, but here I denoted the bipartite graph here. Oh, okay, but bipartite graph is just a graph where the vertices are colored black, either black and white. And of course, some of the people, I'm sure that in the audience will recognize this as the on-shell diagrams for the scattering amplitude of 4-dimensional n equal 4 supersymmetric Yang series. So it's interesting that the same combinatorial graph appears in completely 2 different physical contexts. In fact, it's so different because in n equal 4 context, we have the single series n equal 4, and we have many on-shell diagrams which represent many scattering processes. But each of these different scattering processes are now translated to different gauge theories. So the counterpart of n equal 4 is like really something that goes beyond the single series. But anyway, so this is an analogy. But it's just that the statement that the same graph, exactly the same graph appears here. And well, you could take various viewpoints. Maybe this is a coincidence, and mathematical coincidence, there is no. But except that people have been trying to develop integrable structure on the gauge theory side, which I've been telling. And also we heard from Tomek's talk yesterday that the people are trying to introduce the integrable structure on this n equal 4 structure too. So there is some, right, so people are, and the details are completely different, except that still maybe there is something we might be able to learn. And for that, it's useful to try to understand both sides better. And from the integrable model viewpoint, well, okay, and there's one interesting question, for example. So in this case, in my case, the Yang-Baxter equation is translated some duality, which in the end can be understood from Seiberg duality. But that's interesting because, in a sense, that's a little bit boring in the sense that it follows from known duality. So I might want to find a new duality which doesn't come from the Seiberg duality. And the fact that the Yang-Baxter duality follows some Seiberg duality is that you have this complicated structure, and that follows from some input simpler ingredient which is there. So if I were to make it, to understand things better, I might want to have a situation where the Yang-Baxter equation on the scattering amplitude side is represented in a much simpler way. And in fact, there is such a theory. That's the three-dimensional ABGM theory. So the scattering amplitude of 3D ABGM theory is somewhat similar to 4D N=4, but there are important differences. So for N=4 case, there is a basic building block, is a trivalent block, which is a 3-point vertex. However, in this case, we have a 4-point block. That's the basic building block. There was a distribute 2 here, which somehow deleted. But anyway, and I'm not going to explain the notation. Well, notation appeared in Tomek's talk, and anyway, I'm not going to use it. But anyway, there is a 4-point amplitude. And in a paper which appeared just yesterday, we introduced some deformation parameter here, z, to the 4-point, and also to the other arbitrary points. But for the 4-point, there is some parameter which deforms this here. And there is a corresponding deformation of the Grassmannian formula, where for ABGM theory, we have something called orthogonal Grassmannian, where this is 0. And the statement, well, at least the mathematical statement is that it is invariant under the action of the Yangian for the supergroup corresponding to ABGM supergroup, which is OSP 6/4, with some evaluation parameters related to this parameter z. And so this is the 4-point. And of course, another question is there any counterpart of the Yang-Baxter equation? And in fact, there is. The Yang-Baxter equation really looks like this. So in fact, this is the ABGM counterpart of the on-shell diagram. So for N=4, we have this sequence, and then that's one of the basic moves for the on-shell diagrams. But people have developed the on-shell diagram story for ABGM, and this is one of the basic moves. So in this case, there is no structure like something follows Yang-Baxter thing follows from something more building blocks. But this Yang-Baxter equation itself is really the basic building blocks in this story. And in this case, there is a 6-point amplitude, and this mathematical statement is that, first of all, the top cell of this orthogonal Grassmannian is unique, and consequently, we expect that these things, the product of two, so we have R matrices here and there, we can glue them together in the sense of the scattering amplitude, and actually it follows, well, let's see, we can show that they satisfy the Yang-Baxter equation. So in this context, the Grassmannian integral for R4, this R4, A4, yes, so A4, but which is denoted by R. So that's the reason as a Grassmannian integral, and it takes particular expression in this form. So there is some expression here, but that solves the Yang-Baxter equation, and that is invariant on the Yangian. So, well, of course, there is an interesting question of what's the meaning of this spectral parameter, et cetera, as an application to amplitude. But I also, today I declare that I don't care too much about supersymmetric gauge theory itself, but rather use the supersymmetric gauge theory to understand integral modes better. And so in that sense, this scattering amplitude construction for ABGM seems to give a nice way to give a different expression for R matrix for this particular Yangian. Okay, so since I guess my time is up, so let me try to conclude. So the statement here is that I have a Yang-Baxter equation, but the Yang-Baxter equation is promoted to a duality, which I call the Yang-Baxter duality for obvious reasons, and that's a consequence of Seiberg duality. And this is a very sharp result. And once you promote this result to gauge theory language, you can compute various partition functions to obtain a class of integral models very schematically. And so the statement is that the partition function for this theory, which, okay, maybe I denoted Z previously, is the same, gives directly the integral model. So it actually, the supersymmetric gauge theory directly gives the definition of the integral model. And interestingly, the resulting model seems to be rather general, and there are some mysterious parallel with the different topics like register network, for example, or scattering amplitude. And so the fact that similar combinatorial structure appears in many different places might be suggesting something. And of course, there are many interesting open questions. Well, for example, I just framed the Yang-Baxter equation by the physics argument. But of course, you can try to question whether you can really prove that Yang-Baxter equation mathematically. And it seems to be very hard, but nevertheless, I have a very concrete expression of the R matrix, etc. So in principle, you could be able to prove it, and that'd be interesting. And also, I also mentioned the issue that there might be some quantum group-like structure hidden behind it. So that's interesting. But I could make a somewhat more broader question, which is that since I understand the Yang-Baxter, R matrix in Yang-Baxter equation, Gaussian language, well, can we open the textbook on integral models and then try to pinpoint something random and then try to cook up a Gauge theory counterpart of these statements? Can we cook up the Gauge theory counterpart of the algebraic Bethe, for example? And I'm very far from doing that, but I think it's a very interesting, tempting question. So can we promote it to a duality? What's the meaning of Bethe equation, for example? All these things I think is very interesting. And also, somewhat more conceptually, these things, the story I found seems to suggest that there are some integrable structures, not in a particular Gauge theory, but in the space of quantum field series. So that's a striking result, and then now that motivates us to think not in terms of single quantum field theory, but a set of quantum field theories. And then people have been talking about the potential possibility of new formulation of quantum field theories, and it might be that the integral structure we found here might be useful as a clue as to what the new formulation of quantum field theory is. So let me finish the talk here. Thank you.
You obtained one particular model,
yes.
though it's very complicated.
Yes,
but
yes.
could you obtain some simpler model, like 6 vertex model?
Yeah, okay. Yeah, I mean, so I think, for example, one concrete question which I haven't answered so far is the following. So in your model, so I have this extra integer, but let's set R to 1, and then you have verified that it reduces the Carter Potts model after the degeneration. And then I could ask a question whether I could keep that parameter R integer and then try to do the similar reduction. And does that parameter persist, for example? Do we obtain Carter Potts model with integer R, for example, where it reduces to Carter Potts model with R equals to 1? I have no idea. Maybe that parameter reduces, for example. So
I mean, that Yang-Baxter equation is a particular representation with continuous spin
yes.
on a circle.
Okay.
But there are discrete series, like, well, discrete spin, like spin 1/2, up,
okay.
down, just two state.
Right.
Finite dimensional representation of quantum group.
Right. Yeah.
Can you get it from gauge theory?
Yeah. Oh, okay. But well, I mean, okay. So in order to, well, of course, you have the expression, so we can try to manipulate mathematically, taking the limit, etc. But since I'm a gauge theorist, I might want to do it better, namely to try to understand the meaning of specialization better. And then in that case, I first have to understand what's the meaning of this parameter P and Q when it goes to root of unity, for example. And interestingly, for example, one thing I've been thinking about is that you can try, so the geometry is, say, I could take R equals to 1, so geometry is S1 times S3. And I could take, so that, and with the two parameter PQ, that's known as the Hopf surface in the S1 times S3 for P and Q parameter as a complex structure. Now I could take the limit where these parameters go to root of unity, and then this S1 times S3 blows up into ARE, for example, where the overfolding of ARE related to the root of, order of the root of unity, for example. So it might be related to some version of the partition function ARE space, for example. So that might be my way of trying to understand the reduction and how it's connected to discrete spin chain. And I think it'd be nice to do that. So that's gauge theory way, and also we could try to do more mathematically. And of course, for better doing that mathematically, we also want to identify the quantum group-like structure behind all these things. That's, I think, also extremely interesting.
My question is if you can have a more general for manifold, or there is some kind of limit where
okay.
it's as general as it
Yeah,
gets,
that's also an interesting question. I mean, well, for example, well, in practice, the partition function people have computed are limited, and the length space index is more or less the most general thing. But of course, it doesn't prevent you from doing, well, people have thought a little bit about S2 times D2, for example, and it might give rise to integral model like this. And also, but however, there is one caveat in my story, that these dualities are really IR dualities, so they work strictly in the IR, where the gauge coupling constant is infinity. So if you compute the partition function UV, which is what we do, then they are not actually the same, because they might not be the same, because there is a coupling constant dependence. So the one way to ensure that there is no coupling constant dependence is to compute the index. And that's why I have S1 in the story. So it's an index, it's an independent continuous parameter, which is, in this case, gauge coupling constant. That's what I do. And so, but then if I specialize to that, but there are other cases where you don't necessarily have the circle, but nevertheless gauge coupling constant drops out, like a 3D n equal 2 theory in S3. So I don't exclude that possibility. But let's suppose for the argument that I have S1, for example. And then I have S1 times some 3 manifold, and then try to do that. And now there are not too many possibilities, for example. So suppose that I have a topology of S1 times S3, for example, and a compute a partition function. And people have come up with a general argument showing that the partition function S1 times S3 depends only on the complex structure of the manifold. And people have called AIDA actually classify the complex structure, and there are 2 parameters which P and Q. And in fact, as far as I know, there is also one single, but that's a 2-parameter family. For S1 times S3, there is also a very strange complex structure which is completely isolated as a point. So whose partition function nobody computed, for example. So that might also give rise to something new. But that's you can try to limit the possibilities that way. So if you want to go beyond that, I should go to S1 times S1 times S2, which is more like a T2 times S2, which people are doing. Or take an obifold, for example, to make it more complicated. So I think it's possible to classify all the possible integral models arising from this way using that. Yes. And that's very interesting. Yes.
When you consider the 3-dimensional theories,
yes.
Do you have the interpretation of the 3-dimensional theories as theories on a duality wall? So can you sort of engineer a 4-dimensional theory for which the 3-dimensional theories would represent duality moves?
Oh, okay, I see. That's an interesting question, but at least the short answer is no. Yeah, I mean, that's really the question of whether, right, so I could start 4D n equal 1 dimension with 3D n equal 2 is related to that, right, the boundary theory 4D n equal 2. And I don't have a short answer, and well, I don't have a short answer, and at least I would say if you take a most general theory like this, probably the answer is no, except that there are some indications that there is some connection. Namely, I start with this theory, and the dimension reduced to 3 dimensions, and then you have a partition function, statistical partition function. Okay, so the 4D theory corresponds to statistical partition function on the 2D, and then and then you take the limit where the 3D limit, and then it turns out that you can the resulting partition function uplifts to 3 dimensions as the sum of the polytopes. It's a sum of logarithm. That's sort of obvious, but it turns out that sum of logarithm can be interpreted as a sum volume of some hexahedron actually living on the 3 dimensions. And we haven't verified any quantum corrections to that story, but at least in that case there is some indication that the 3D limit corresponds to Chern-Simons. Yeah, I mean hyperbolic geometry in that sense. And so the question, one way to try to answer your question might be to relate that story to the other story of 3 manifolds versus 3D n equal 2 gauge series. And that I think has not been done yet.